Look at the equations that govern our universe, from classical mechanics to quantum dynamics. They almost all rely on an external, continuous time parameter, denoted as t, to calculate how a physical system evolves. Removing the time parameter shifts the description of physics from an evolving timeline to a sequence of spatial configurations. The equations now map a shape space, a landscape defined solely by the relative positions and angles of matter. This challenges the standard interpretation of modern physics. For over a century, the working assumption has been that time is fused into an objective, geometric fabric known as spacetime. But a strictly relational view suggests a different starting point. It posits that time possesses no independent, objective existence in the physical universe. It does not flow in the background, and it cannot be warped. Instead, time is a measurement we derive. We track regular, cyclic changes in a localized system, like a clock, and compare them against the non-repetitive changes happening in the rest of the universe. Rethinking time as a derivative of change provides a framework to address the long-standing tensions between the smooth orbits of classical physics and the static constraints of quantum gravity. This relational approach traces its roots to physicist Ernst Mach, who argued that inertial properties are determined by the relative distribution of matter, rather than rotation against an invisible absolute space. We see this realized in classical mechanics through Jacobi's action principle. This equation determines the path of a system through its configuration space entirely through spatial variables. There is no t in this formulation. The duration we experience is extracted after the fact. It is the ratio of the system's total physical displacement to its relational energy. If the components of the universe do not move, time evaluates to zero. Scaling this up to cosmological gravity requires moving past the standard Hamiltonian formulation of general relativity, which relies on slicing a four-dimensional manifold into many-fingered time. Theoretical physicists replace this through symmetry trading within a framework called shape dynamics. This trades the ability to slice time differently for the ability to change the local scale of shapes. Under shape dynamics, gravity is a relational transition between three-dimensional spatial geometries. Physical change occurs as these intrinsic shapes smoothly transition from one configuration to another. These shapes are ordered using York time, a metric derived from the global volumetric expansion of the spatial geometry itself. It is an internal measure of change, not an external ticking clock. By extracting duration from the geometry itself, gravity becomes a sequence of evolving shapes. This offers a path where a substantive four-dimensional space-time continuum is no longer a foundational requirement. If we move away from a four-dimensional fabric, we must account for the highly precise, empirically verified effects of Einstein's time dilation. The geometric interpretation claims that a moving clock physically traverses a different length of a temporal dimension. In a relational universe, time dilation represents the physical retardation of a process. In this split screen, the right side shows how velocity and gravitational stress physically alter the internal dynamics of a system. Placing a cesium-133 atom in a dense gravitational potential suppresses the rate of its internal interactions. It requires a longer duration, measured against an unperturbed external clock, to complete its hyperfine transition. This physical retardation accounts for the exact synchronization requirements used by global positional satellites to maintain accuracy. As a system translates through these fields, the rate of its internal repetitive changes must decrease to preserve the constant speed of light and the stability of causal structures. Time dilation is effectively an environmental constraint on the physical processing speed of local clocks, preserving Einstein's empirical predictions within a timeless space. This framework also addresses a major hurdle at the boundary of quantum gravity, the frozen formalism paradox. When physicists apply quantum principles to general relativity, the Hamiltonian becomes a constraint that must vanish. The resulting Wheeler-DeWitt equation indicates that the quantum state of the entire cosmos does not evolve. From a perspective outside the universe, absolutely nothing changes. The global state is a static entanglement of all possible structural configurations. To recover the evolution we observe within this frozen state, physics uses the Page-Wootters mechanism. This mechanism divides the Hilbert space of the universe into two interacting subsystems, a clock and the rest of the universe. Though globally frozen, these two systems are deeply entangled. An internal observer uses this entanglement to ask a conditional question. What is the state of the universe given the clock is in a specific state? Through this mathematical projection, the rest of the universe is shown to evolve. This emergent evolution is strictly conditional, existing only relative to the localized quantum clock state. At the fundamental level, time is not a background rhythm. It is a local property generated strictly by the entanglement structure of internal subsystems. If time is relative change, we must still explain why that change appears to have a preferred irreversible forward direction. The thermal time hypothesis addresses this by framing the arrow of time as a thermodynamic illusion. Macroscopic observers cannot measure every microscopic variable. We interact with coarse-grained statistical states instead. This statistical ignorance mathematically generates a unique modular flow within the system. This flow, generated by the system's thermodynamic state, is exactly what we perceive as the passage of time. In practice, we measure this flow with real physical clocks, but every physical clock is a quantum system subject to its own fluctuations and uncertainty. Using these imperfect clocks to measure other systems induces what is known as fundamental decoherence. Because the clock itself fluctuates, the off-diagonal terms representing quantum superpositions decay. This permanently suppresses macroscopic superpositions. The forward arrow of time and the collapse into a definite reality are simultaneously born from our thermodynamic ignorance and the inherent flaws of measurement. A strictly relational universe requires a new definition for the reversal of time. Without a temporal axis, reversal cannot be passive. It's an active physical operation. Look at this shattered glass. Reversing time means actively inverting the physical momentum of every atom, forcing the system to retrace its spatial shapes against entropy. This changes our understanding of the past. It is not a geographic coordinate that currently exists behind the present moment. The past is a structural configuration of matter that has disbanded. It remains only as memory physically encoded in the records of our current shape. Consciousness interfaces with this reality as an internal clocking mechanism. It correlates internal neural rhythms against a changing environment to track relationships in the cosmos. Time is the epistemic shadow cast by the relentless material transformation of the universe. Reality is an active computation, not a pre-drawn map.